we're going to learn about one new derivative rule. Okay, just one this time. This is something we have not learned yet, and that is how to take the derivative of an inverse function. Okay, so we're going to start with a little talk on, just a little refresher on what an inverse is, and how to find it algebraically. And then we'll get into why the rule is what it is, and just add this to our list, of all these derivative rules that we know. So, basically what a derivative is, it's where you have a relationship between x and y, and you reverse that relationship so that all of the elements or the values in your domain become elements in your range, and vice versa. So, if you have a function that has inputs and outputs, and if you invert that function, what you're doing is reversing what the inputs are and what the outputs are. In Algebra 2, you learned how to find these inverse functions algebraically. And basically what you do is you take that idea of reversing the inputs and outputs. So like in this case, our inputs are x and our outputs are y. But if we want to find the inverse of that, we would flip what our inputs and outputs are. And so in this case, our inputs would now be this variable, and our outputs would be this variable. And so what we're essentially doing is just swapping x and y. And then to actually come up for an explicitly defined equation for y, we need to solve for it. So we would add 12 to both sides, right? And then we divide both sides by 3. And so we get this equation y equals x plus 12 over 3. Okay, now this is the inverse of the original equation, and we don't want to confuse like what's x or which y is which. So we've got this notation that we use. It's a little bit of an unfortunate notation, I think, because it already means something in a different context. But basically, you're going to put a little -1 in front of that function. And yeah, I know that also means like raised to the negative first power, but those two things don't mean the same thing. An inverse is not the same thing as a reciprocal. So it's like I said, unfortunate that the notation looks exactly the same, and most often you just have to use context to know whether you're talking inverses or reciprocals. But in this context, we're talking inverses. And so basically what's happening here is any point that's on this original equation, like if I plug in 0, I get -12. So 0, -12 would be a solution to this equation. But if I flip that and do -12, 0, that would be a solution to the inverse. Sam, did you have a question?
You can just rewrite that like x over 3 plus 4, right?
Yeah, you could rewrite that as like 1/3 x plus 4 or x over 3 plus 4. Absolutely, yeah. So now, sometimes you can rewrite the inverse explicitly, and in this case, that would only be possible if the inverse is a function of x. Sometimes the inverse is not a function of x, and so you cannot write it explicitly. Like if I take a look at this quadratic, if I swap x and y here, we're going to run into an issue where after I subtract 5 from both sides and divide both sides by 2, I'm going to have to take the square root of both sides. And what happens when you take the square root of both sides of an equation is, well, the square root of y squared is the absolute value of y. It's not just y. And therefore, we're going to have this plus or minus thing happening. So y, or at least the inverse of y, would be plus or minus x, x minus 5 over 2. The plus or minus the square root of x minus 2 over 2. Minus 2. Minus 5. There we go. That looks a lot better. And so this is, in this case, y is not a function of x, because there are going to be many x values that we plug into here that would have 2 different y values. And that's not like necessarily like bad or not okay. That just means that the inverse is not a function of x. If we try to like think about what the graphs of these two functions look like, the original is a parabola that shifted up 5 units, right? And so this inverse is going to look something like this, right? It's going to fail that vertical line test. And that's, this whole plus or minus thing is, if we take all the points that we would get if we, take the plus, that's going to be all the points that are on the top half of this parabola. And everything that the minus is going to be the bottom points on this little sideways parabola. So anyway, you can have an inverse that's not a function, I guess is my point. Now, if we wanted to try to differentiate this, we'd probably be better off using implicit differentiation and trying to write this as an implicitly defined equation rather than an explicit one. But we'll get to all that. So just to kind of really put it together, okay, if you've got a point 3 comma -8 that's on a function, then the point that's going to be on the inverse, so like if this is on, we'll say f of x, then the point that's going to be on the inverse of the function, f inverse is written like this, you're guaranteed -8 comma 3, yeah, very good, is going to be on that inverse. Right, because basically every point that's on the original function, if you swap x and y, that's going to be a point on the inverse. And that's actually what an inverse is. You're literally inverting the x's and y's. Okay, so that's a little quick review of Algebra 2 there. But let's get into the, why we're all here, which is to find out about the derivatives of these things. So I want to try to show you why the derivative rule is what it is. I know we don't do this for all the derivative rules, but I think sometimes it's valuable. So let's just assume that f and g are inverses. In other words, g we're defining as the inverse of x. Okay, so we're just going to let this be true. And one thing that is true about inverses is they undo each other, like multiplication and division, addition, subtraction. These are inverses. Like if I were to say, let's solve this equation, x minus 3 equals 9. To solve that, we would invert the equation. We would add 3 to both sides because addition is the inverse of subtraction. Square roots, I guess that's not a good example, but in just kind of in a simplistic way, square rooting and squaring kind of undo each other. Okay, if we ignore the whole plus minus issue. And so anyway, so inverses will undo each other. And so what happens when you take the inverse of its own function? So like if I say f inverse of f of x, so if I invert whatever's being done, what I'm going to be left with is just x. Okay, and this is true whether you take the inverse of a function or if you take the function of its inverse. In other words, it doesn't really matter which direction or which function you're applying to which inverse, one way or the other. You're both going to be just left with x. Okay. So we've got those two facts established, and so we're going to assume f and g are inverses. Well, if we can assume that they're inverses, then we can assume that f of g of x is x. Right? This is a statement we're allowed to make because we're assuming those two functions are inverses.
Why is it assuming and not knowing?
Well, so in other words, like f and g are just letters, right? So I'm telling you that we have these two functions, and let's assume they're inverses.
Okay.
Yeah. So it's really just how you start with a proof is you need some kind of given information. Like what are we going to start with here? Okay, so if this is true, what we can do is we can differentiate both of these because we know how to use the chain rule, right? So let's differentiate both the left and the right-hand side here. And so we know how to handle the chain rule on the left-hand side, right? This would be f prime of g times g prime. What's the derivative of x? 1. Yeah, good. Now, what I'm trying to find here is the derivative of the inverse. So I want to come up with hey, if I have this inverse function, I want to know how to find the derivative of it. So what we're really trying to find here is the derivative of g, because g is, we're assuming, the inverse of f, right? So if I isolate g prime here, that should be our rule for the inverse of f. So to isolate g prime, we just need to divide both sides by f prime g. And so we get g prime is 1 over f prime g. And that's your rule for finding the derivative of an inverse. Okay, another way of looking at this, now this is only going to be true, make sure, if g is the inverse of f. Okay, so this is not just like, this doesn't work for any f and g. This only works if g is the inverse of f. So if we want to not refer to g and just talk about f and its own inverse, f, the inverse of f, we could rewrite this as the inverse of f, remember that's just g, that's how we define g to begin with, is equal to 1 over the derivative of f of the inverse of f. And so a lot of times you'll see it written like this, although I kind of like having the f and g just because we already have so much experience with the chain rule already. So either one of these, how you want to think about it, is fine. Oh, wait a minute. I didn't have the inverse on here. So yeah, we need the inverse. Excuse me. Yeah, so the derivative of the inverse. God, yeah, so I had the inverse notation, did not have the derivative notation. And so this rule is actually already up there on the board. It's the very last one on there that we'll learn for now. Okay, so any questions about the actual rule for finding an inverse, finding the derivative of an inverse? Now, let's take a look at some examples here. All right, so this one says we've got a function x cubed plus 2x minus 1, and we know that f of 1 is 2. So find the derivative of the inverse of f. Okay, this is the derivative of the inverse of f. Okay, and this is at x equals 2. So we'll have to evaluate it when x is 2. Now, let's, out to the side, we'll just say anyway, so we'll let, sorry, not f, let's let g be the inverse of f. And I think writing it as like its own letter will clean up a lot of the notation. We just have to remember that g is the inverse of f at the end of it all. Okay, so if that's the case, then if f of 1 is 2, that means we have a point on f, 1, 2. What point is then going to be guaranteed to be on g? 2, 1. So g of 2 is 1. Okay, we'll also need that piece of information. All right, so let's first find the derivative of f, because really, if we're going to use this this notation, say this is g prime. Sorry, this is the inverse and the prime notation all whacked out. Okay, there we go. So we want the derivative of g, which is the inverse of f. I think I got that straightened out. So that's going to equal 1 over f prime of g. So if I want to evaluate this for where x is 2, okay, the instantaneous rate of change at 2 will be 1 over f prime of g of 2. Now we already know what g of 2 is, but we're going to need to know what f prime of that is. So that means we got to find f prime. So f prime, using the power rule, is going to be 3x squared plus 2. Okay, so now let's go ahead and try to evaluate this derivative. So the derivative of the inverse of f at 2 is 1 over f prime of, now what did we say g of 2 was? 1. And now we can evaluate f prime of 1. Yeah, because we have f prime. So f prime of 1 would be 3 times 1 squared plus 2. So that would be 5. So this would equal 1/5. So a couple of things that I think maybe just to really solidify this, one suggestion I have here, and this I think will help when you're doing these inverse problems, is actually just give the inverse a name. Instead of writing it like f with a -1, say, okay, it equals g, or just give it a name. And I think the algebra just works out really nicer that way if you do it. Any questions so far? Okay, let's do another one. Okay, number 2 says the function f is defined by this function, and we've got a point on the graph of f, and we want to know what is the derivative of the inverse of f at -10. So this is really the same question. Okay, if 2 comma -10 is on the graph of f, what's on the graph of g?
-10,
Yeah, -10 comma 2 is on f inverse, which is g. So if I want to find the derivative of g at -10, I need to find the derivative of the inverse of f. Okay, so we've got 1 over f prime of g of -10. Now what's g of -10? Okay, so this is going to be 1 over f prime of 2. And so now we'll need to find f prime so that we can evaluate f prime of 2, and then we'll have our answer. So f prime, using the power rule, would be -6 x squared minus 1. Okay, now we can evaluate that at 2. So f prime of 2 would be -6 times 2 squared minus 1. So what is that going to be? -24 minus 1 is -25. Okay, so this will equal 1 over -25. Any questions about number 2? All right, last one. We've got a table for f, g, and f prime, and it says if g is the derivative of, sorry, not the derivative, if g is the inverse of f, then we want to know what's g prime of 4, what's g prime of 6. So if we want to know g prime of 4, g prime of 4 is going to equal 1 over the derivative of f of g of 4. Now, we don't see g anywhere in this table. So what I would recommend is you construct a table for g. Okay. So we've got x and we've got g. Remember that g is the inverse of f. So what we can do is take this table for f and just flip all the values, and then we'll have g, because g is the inverse. So we have like 4 comma -2, 6 comma 0, 7 comma 6, and 10 comma 4. And so if I want to evaluate g of 4, now I've got that value. Okay, g of 4 is negative 2. So 1 over, well, that's ultimately what we want to find.
Yeah, no, I forgot.
But in order to evaluate that, we need g of 4. Because we're not really going to be able to find g prime without going through that formula. So yeah, we've got f prime at negative 2. And we could find that value in the table as well. F prime of negative 2 is 4. So this would be 1/4. I know we're kind of pressed for time here. G prime of 6 would be 1 over f prime of g of 6. We can see in the table that g of 6 is 0. And f prime at 0 is 2. So this would be 1/2. Okay, that's it for today. I'll go ahead and try to quickly get your homework so that you guys can do it by the time